Let me ask you something. Have you ever charged your phone, switched on a flashlight, or watched a piece of iron slowly turn reddish brown in the rain? These might seem like unrelated events, but they're all connected through one fascinating area of chemistry: electrochemistry. Electrochemistry is the study of how chemical reactions can produce electricity and how electricity can, in turn, cause chemical changes. And guess what? It's not just confined to labs or textbooks, it's happening around you all the time. Take a simple battery, the kind you find in your remote or a torch. Inside that small cylinder, a chemical reaction is occurring. One material is losing electrons and another is gaining electrons. This movement of electrons creates an electric current that powers your device. This kind of setup, where a spontaneous redox reaction produces electricity, is called a galvanic cell or voltaic cell. A common example is the Daniell cell, which we will explore in detail shortly. But for now, remember, wherever electricity is produced by a chemical reaction, electrochemistry is at work. Now let's flip the idea. What if we want to use electricity to create a chemical change? Imagine you have a beaker filled with salt water and you insert 2 electrodes into it. If you pass an electric current through the solution, you can produce gases like hydrogen and chlorine. This process is called electrolysis, and it's used in industries to produce elements like sodium, magnesium, and even chlorine gas. So electrochemistry works both ways. Chemistry can create electricity, and electricity can drive chemical reactions. Here's something even more amazing. The signals that pass between your brain and body, your heartbeat, your muscle movements, all of that happens due to tiny electrochemical signals. Ions like sodium, potassium, and calcium move across cell membranes, generating small voltages. It's nature's way of running electric circuits inside your body. So yes, electrochemistry is not just science. It's life itself. In this chapter, we will explore, first, how a galvanic cell works, how the spontaneous transfer of electrons creates a usable electric current. Second, we will understand the concept of electrode potential, why some metals are more likely to lose electrons than others. Then, we will learn how to calculate the electromotive force of a cell using the Nernst equation. That's C equals E naught minus 0.059 by N multiplied by log of concentration terms. We will also cover how ionic substances conduct electricity, how to measure conductivity, and what molar conductivity means. Later, we'll apply Faraday's laws of electrolysis to calculate how much of a substance is deposited or released during electrolysis. And finally, we will study real-world devices like batteries, fuel cells, and even learn how corrosion, like rusting of iron, is actually an electrochemical process. So why should you care about electrochemistry? Because it connects deeply with our lives, from powering your home to understanding your own body. It plays a role in green energy, industrial production, medical science, and even climate technology like fuel cells and hydrogen energy. Understanding electrochemistry opens the door to solving real-world problems. And in this chapter, you won't just learn equations, you'll understand the science behind the sparks. So let's begin this journey, step by step, and uncover how chemistry flows as current, powering the world around us.